I want to say thank you for coming. And today we're going to be making a presentation that involves 4 of us. So it's lots of quick little information bites that you're going to get. It's from the agricultural economists that work in the primary industry development. We work within this pillar, but we also do a lot of work across other with other pillars as well. And this is a wonderful opportunity to present something that started literally from past experience and knowledge that we had at the department. And we made a tool or a model or a spreadsheet that didn't exist. We managed to build it because we secured the services of Sudarshan Kharel is his full name. And he started this process of building our mind's eye, our wish for a model that did not exist before. And previously we've had other models and we've learned a lot from using them. We've had MIDAS model, which is a whole farm model. We've had gross margin models. But we needed a model that took the current knowledge of what we know about growing crops, their agronomy, and also pasture and livestock grazing and how that's integrated on farms in WA in the wheat belt of Western Australia, ranging from farming systems that go from Geraldton to Esperance. But we knew that it was going to be far too complicated to do it at the whole of farm level. So what we did is we built it on a field by field basis, paddock by paddock basis. So this tool allows you to have a look at a field, a representative field. You can choose its parameters of how big it is and or where it is, in which agroecological zone it is, and what soil it has, and all of that sort of stuff, and what rainfall it's going to experience, and simulate what might happen if you do different things to it. So this is a collaboration between Sud, Brad, Christophe, and myself. Christophe is a new team member, and he's come in and taken the eValues model that we built, this paddock level model that integrates, hopefully coherently, all the different elements of fertilizer application, lime application, plant growth by time over different seasons, the money side of things for growing these things. And Christophe came in and helped us put in the greenhouse gas emissions into the model. And he's now also going to be looking at integration of trees onto a paddock, like is being modeled in eValues. So he will start by putting in the tree that we know most about, which is the Mali farming system, the tree belt system for biomass, for biofuel, which has its own concomitant benefits, but he can talk about that later. Now, you might remember that Dempster and Gazy and others, Davies, wrote about the different ways that we can manage land, and we can also add things to land, ameliorate the land or do inputs on the land. From everything from zero tillage to worm juice. And so they go from conventional farming all the way to regenerative, whatever else you want to call it. But the scientists working at this department for the last 40 years and beyond, before that, and our collaborators at various universities around Australia have worked on these issues, the issues of tillage and fertilizer and time of sowing and everything else. So I won't go through the whole list, but Gazy et al. Actually looked at this and said, well, parts of this are parts of sustainability issues in agriculture, and regenerative agriculture is taking some of these things. And so you can read that paper and very profitably several times to learn about what they're saying about regenerative agriculture. I won't go on about it, but we want to have a model where these things can be evaluated. What happens if we switch between synthetic fertilizer to legume pastures rotated with cereals? We haven't had a model for a long time that can do that in over a 15-year period. What happens if you include, you add lime to the soil? We've had lime and other similar models, but we wanted to put all of this together with fertilizer, with soil type, with different regional rainfall, issues. So hopefully you will see that the model that our team is going to present to you, called E-values, is doing a coherent integration of lots of things we know. So what's really important is how variable our environment is. So this is rainfall. Of course, the blue stuff is the growing season rainfall that people rely on in the wheat belt. This is for M4 in the agroecological zone around Kulin. And the brown stuff is the rainfall of the summer. And you can see what a crazy roller coaster that is. And a farmer living from 1996 to 2020 is going to have to manage this, because this is what's impacting on their yield and by extension their profitability. Then you can see the grain prices on the left-hand box varying crazy. So green is TT canola, blue is wheat. They all go up and down, and so is barley. They all move in significant ways, which also then affects your profitability, because you put the crop in hoping to get X amount of profit, but what you can sell it for is a different matter, because the seasons have different seasonal prices. The lamb prices are the purple bars. You can see they vary a lot, and wool price used to vary much less, but it is becoming more and more variable now. And that's at the bottom right-hand side, the blue bars is the wool price for 21 micron. That is to say that, so I'm trying to say that prices vary a lot every season for a wheat belt farmer. The weather varies a lot for a wheat belt farmer, and the farmer has to then play this game against a non-malevolent opponent called climate and market, because we are price takers in this system, and they have to manage this farm. You can see at the bottom is the whole of the farm with the different soil types imposed on it, and each box is a paddock. And that paddock has to be managed through time, which is the diagonal stuff moving from the bottom to the top right-hand side of the screen. And you want to be able to say something about the economics of this for different agroecological zones. Now, we know that we're not perfect. We can't model this system perfectly. But the idea was, can we capture the essence of this with the current contemporary knowledge of the system from the various scientists that we've got in the department or at various universities, and then put all this together and say, which system makes the most money? Which system generates the most amount of greenhouse gases? So this graph is very quick. It's showing you the profit on the x-axis and the variation of that profit, or coefficient of variation, on the horizontal axis. And you can see that things in the last, between 2005 and 2019, in a place that we have modeled with this, which is the M4 region, this is the kind of things you could get. You could get barley legume pasture rotation, making you about $150, which is the second one on the left. And it would have had far less variability in profit than if you grew continuous wheat, which is the bottom right-hand side, making you only about $75, $100 difference. But this is for this one particular case study farm that we looked at. And of course, we can examine the assumptions that go behind all this, and there are many, but we wanted a tool that could do this. Now, I'm not saying this graph is perfect, or this is exactly what every farmer would get, but we wanted a tool that could tell us the risk return scenario. We wanted this, later on we thought to ourselves, once Sudarshan made this tool, we wanted to say, well, what about greenhouse gases? Now that we have the climate resilience team and its resources enabled us to put some effort into this. On the horizontal axis, we've got the gross margin or profitability of the land uses. And on the vertical axis, we've got carbon dioxide equivalent emissions. And as you know, fertilizer has different weighting on emissions than chemicals and fuel. So we put all that in with the help of both Sudarshan and Christophe. And you can see that the situation changes. A continuous legume pasture with sheep grazing it emits most about nearly 1200, whereas continuous wheat emits less. So you got this trade-off between profit and greenhouse gas emissions. Yeah, something that makes less profit also tends to emit less. But so if you go for something in the middle, like wheat, barley, canola, which they practice around Kulin, you get this situation where you're emitting, you are generating about $110 a hectare on average over a 15-year period, and you're emitting much less than you would do if you did barley legume pasture. So this way we can help scientists live with us, working with us, or we can help any farmers or farm consultants see that what the trade-offs are. So if you drop $50 in annual profit of that rotation, how much less greenhouse gases would you emit? But you need to change the rotation in order to emit less. So we need to be able to tell a story that is coherent in knowing how wheat interacts with barley, how barley interacts with field pea, and how field pea gives us the nitrogen for wheat the following year, and so on. And the cycle repeats itself. Volunteer pasture doesn't fix anywhere as much nitrogen as a legume pasture does for barley. So they have different greenhouse gas emissions. So what do you drop in profit for a reduction in greenhouse gases? And because you have more, if you have good pasture, you also have more sheep on the land because you can carry more sheep. If you have more sheep, you emit more. So this model allows for all that to be said. And then we can do calculations like this, where we can say the rotations are on the vertical axis, and at the bottom, you've got kilograms of greenhouse gas emissions per dollar of gross margin or per dollar of profit. So you can see that continuous legume pasture emits the most amount of greenhouse gases for every dollar of money we make with it, with that rotation. Whereas wheat, barley, lupin, or wheat, barley, field pea has the least. Why? Because field pea fixes nitrogen. You don't need to apply so much nitrogen. And so on and so forth. So you can look at trade-offs this way. And you can see that this model can also tell you how each of these rotations has different amounts of greenhouse gas emissions, but the proportion of the greenhouse gas emissions that you emit for that particular rotation or attribution you can make is to different things, like continuous legume pasture. 91% of the emissions come from livestock, this one in the middle. Whereas if you grow wheat, barley, field pea, there is no livestock in that particular growing season. And then fertilizer, chemical, fuel, and other things are part of the mix of greenhouse gases. And you can see chemicals become quite important in that system because you need to control the weeds and the diseases. But wheat, barley, canola, chemicals and fertilizer are on an equal basis. Field pea needs more chemicals to protect it from bugs and weeds. So, and fuel is not as big a component as chemical and fertilizers. You can see that, right? So this is the beauty of what these guys have made for us. We're very lucky to have them. We're very lucky to have been given the resources by the Climate Resilience Initiative. And I'm really pleased to see these results coming out, and Sudarshan did this for me last night, so I thank him for it. And we can also monitor the soil organic carbon. You can see that between 2004 and 2020 on the same sort of land, wheat, barley, canola, if you practice zero tillage, doesn't lose a lot of soil organic carbon. In fact, it puts on a bit of weight. So from about 13 tons, you get about 13.1 tons of carbon per hectare. But in the top 10 centimeter, but pasture barley builds the soil organic matter more. So please pay attention to the fact that we're not starting the vertical axis from zero. So it's a bit exaggerated. You know, they always say be aware of an economist who doesn't start his axis from zero. So, yes, Ross.
Can you just go back one slide? I just think for people in the audience, it would be useful for that slide to be visually different. That is, rather than each row ending at the same side, for each row to actually describe the magnitude of emissions that come from each hectare of that.
Sure, that's another one I could do.
I think that would be a more accurate way.
Yeah, so you want these sort of numbers, which is on the vertical axis for each rotation. Yeah, but put on the bar chart. Yeah, no problem. That can be done too. Yep, absolutely. But already I have taken far too much time. I just wanted to introduce my team, and I wanted to say how pleased I am that you came and how pleased I am that I have this team to do this for us. So over to whom? Sudarshan? There we are.
Okay.
Thanks, Ross.
After that, quickly, Amir forgot about it, so he didn't take more time. But that is basically conceptual framework of the model, about how the model works. So basically what we were trying to do is have a look at rotation for 15 years and the things that model takes into account. So something like if you're growing wheat, maybe the next week you're carrying on the disease, carrying on the weed. But if you're growing lupin, probably or not, you're providing nitrogen, and then maybe so various things. So basically, which is if you guys want to have a look in the future, go for it. It's too tedious to look at stuff. Cool.
I mean, obviously it's been seen once, it's got paper on it, but.
So this is we drew on Brown Boyle's work.
Okay.
So we don't just make up numbers. we have sometimes. Brown Boyle numbers, and we compare them upwards.
I think it's important to recognise that's from one scenario, from one paddock, one set of conditions.
From one farmer's way of doing
Because
it.
we all use, well, they all use mini and they're not seeing mini green bin.
We don't know what the pH is.
So that's going to be the wheat, barley, and canola.
Well, the graph is.
So well, wheat, barley, canola, if you have a look at the percentage number, that's from the start 0.8%. And by the end, after 15 years, you're raising 0.82%, which is nothing.
Yeah, so it's 0.02% increase in. So it's quite low.
Yeah, well, even the other one.
Right.
Jackie has a point. I mean, if that's substantial, okay. How about going in 30 years, 40 years, 50 years? So it's going to plateau at some stage.
Yeah.
So it's not a continuous increase. So someone looking at that chart might interpret that you are actually going to recommend this to increase soil organic carbon, which is not the case. Which, if you go back in 15 years, 20 years, our farmers have been growing wheat, barley, canola, lupins, all those things, and the soil organic carbon has not increased. So we got to consider this when we present that chart.
Sure. The point of our presentation is to say we have a working prototype. Now, please come and throw rotten tomatoes at it, and let's see if we can defend their assumptions.
Look, I should have used the first sentence to say that great work.
Yeah.
It's not complete. I understand and appreciate that.
I'm conceited enough to know that it is great work.
Yeah.
But I'll let Sudarshan.
So I did a bit of case study, kind of just in case if there is a carbon tax, which probably won't be till 2026 for canola. But what if there is a carbon tax on all the crops we grow? Australia wakes up one day and he's like, all right, we're going to put some carbon tax on that. I mean, he can do that. He puts children on the what is that, forklift. You never know. So, all right. So the case study I did was for low rainfall 3 using Meridian's weather data and from using the price data from 2005 to 2019. And I did a case study in 2 different soil types. One of them is sour sandy duplex, sandy deep sand, and having a look at how does use 4 different carbon tax. So the first one in orange is applying no carbon tax at all. The green one was ACCU's price, Australian Carbon Credit Unit price in December. The yellow one is the European carbon price, and the grey in December, and the grey one is the current carbon price in Europe. So that is no $40 was ACCU's price in December, $100 was European carbon price in December, and 125 is the current European carbon price. So basically, if you have a look at both graphs, as the ACCU's price increase, as the carbon tax increases, the gross margin per hectare will decrease. Because of the fact all of these crops are emitting carbon, so we'll have to pay for that. But one of the main key messages is so you have the gross margin in the horizontal axis, while the land use sequence in the vertical axis, wheat canola, wheat lupin, and wheat lupin. So the number up here is the difference between gross margin with no tax and the gross margin with the highest tax. So the key message is those land use sequence which has more lupin will have a lower difference in the gross margin because of the fact that legume is putting the nitrogen, and then you won't be using as much fertilizer, which will decrease your carbon footprint. Hence, you'll be paying lower carbon tax on those things. The next slide is the kind of same slide, but just having a look at how does different land use sequence, just basically the same thing, but just changing the labels. About rather than comparing the carbon tax, now we're comparing the land use sequence. So as you can see, in the same format, equivalent gross margin in the horizontal axis and carbon tax in the vertical axis. So the blue one is wheat canola, orange is wheat, followed by wheat lupin, and yellow is wheat lupin. So one of the main thing you can see is if you have a look at that, the very first one, wheat, and wheat lupin are pretty similar in context of the gross margin when no carbon tax is added. But when more carbon tax is added, wheat lupin starts becoming more profitable because of the fact you're emitting less carbon. And the same thing with the deep sand, where wheat canola is almost as profitable as wheat lupin. But as you go further with more tax, your wheat lupin will start to become more profitable because of the fact you're emitting less. Yeah. Just wait for Darshan to have a look. Yeah. And this one is more kind of like, as we know from 2026, roughly the canola, there will be a carbon tax on canola, and almost 95% of our canola goes to Europe, which means either we or the importer in Europe will have to pay a carbon tax. So what I did a case study was just having a look, what if there is only carbon tax in canola? Well, none of the other crop are have to pay a carbon tax. So basically similar reaction is the carbon tax. So the first one is no tax, $40, $100, and $125. As the carbon tax increases, the gross margin decreases. But one of the main thing I would say is canola won't probably be replacing in those paddocks where you can grow a really good canola. But when it comes to the other paddock, where canola is just slightly more profitable than other crops, then that's where you might start to see a preference in the other crops, maybe the legumes. For example, deep sand, where canola was slightly performing better than the wheat lupin. After the tax, it fell down to $186 a hectare. What with looping is still, there was no tax on that. Or even maybe it might start coming closer to something else like wheat. That is the key message in that. And finally, just having a look at where does the emission comes from. So something like a crop, a wheat canola rotation, you have higher emission than the wheat with lupin rotation compared to 675 kg and 511 kg of carbon dioxide equivalent per hectare per year. And one of the main place where you get your emission is from fertilizer, followed by the chemical. So fertilizer accounts for 270, almost 32%, and comes about the crop residue and the limes. So in the model, one of the assumptions we have made is we are always liming 1 ton per 6 year. Every 6 year we're liming ton. So if you have a look in both of the rotation amount, your emission from lime is same. And amount of emission from your fertilizer, fuel and electricity is about the same, but crop residue about the same as well. Atmospheric deposition just a bit slightly higher for wheat canola, and chemical same. And the main thing it comes to is how it changes the fertilizer emission from the fertilizer, and that includes all scope 1, scope 2, and scope 3 emission. And if we are bringing in the livestock in the model, we'll probably have a higher emission because of the fact that there is a livestock and enteric fermentation.
So when you say fertilizer, do you actually mean nitrogen or do you mean?
Not nitrogen-based fertilizer.
You actually mean nitrogen?
Yep. The volatilization of nitrogen and nitrogen dioxide gas emission from that, and then that into greenhouse gas. I'll give it to Brad.
Oh, go ahead.
So, another prong of the work that we've been doing is to deep dive and try and understand from a farm whole system what some of the challenges around climate resilience and the issues of sequestration and emission in the context of particular case studies. So that one, isn't it? So the question, the case study that we're working in particular at the moment is structured around this particular question of can the development of a low input, high margin, climate resilient farming system, which is a lot of what this chapter is aiming to do, and is a large part of that down, lower its carbon emissions and increase the carbon sequestration. Question a lot of people know. There's a working draft. It's very near ready for selective release around the department for comment and input from all the wonderful and knowledgeable people we have here. And the protocol by which these things are developed is one that I've developed over 25 years of writing business case study, which is, at the end of the day, the final editing rights reside with the case study of the subject. That creates the high trust process that's needed to be able to go into depth with these things. Just a brief description of the business. It's an expanding business, continuing to grow, so it's generating the capital it needs to do. That's in Coolin and the M4 region. Heavily impacted by frost. That don't do wheat anymore. Barley and oats are 2 crops that are grown. It's a 50-50 crop livestock system. Increasing livestock used to be 70 crops, now it's 50-50. It's going to go to 2/3 livestock over the next couple of years. One of the big pushes on that, of course, is the very high price of nitrogen at the moment. It's a low input hybrid system, is the way that they describe it. It's a mixture of conventional and a certified system that they have for Australian Sustainable Produce. It's a ACCC certified system, so it's vetted, verified on an annual basis. The application of nitrogen slides down over time from 23 units is what they use when they're renovating the paddocks that they're bringing into the system to, at the moment, the uniform application is 7 units, and they're aiming to get that down lower again. And this year, I think the yield for 3.5 tonnes. So on an average year, it's not much. You're depending obviously in a big year like this year, they'll show up. Again, this low input system, they've got very well maintained older machinery and don't have a big cropping program. They don't have the pressure on. So maintenance with old machinery does very well. They use a lot less chemicals, 20 to 40%. Big emphasis on nutrition and soil chemistry. So a big living program and application of a lot of trace elements, liquid calcium carbonates, all over the place. Their pH has improved dramatically to depth. That's the key thing. That 60 centimetres there got to 5.5 pH. Big stress, as I said, on nutritional supplements, traces, links, nutrient recycling from depth. And they have 100,000 unharvested mallee trees. So this was a farm that was very interested in that system some time ago and go and have this legacy of 100,000 trees, which is, again, Christophe will briefly talk about it, one of the reasons why we're building into the values model, the ability to be able to assess the impact of growing trees and then what it means for the farming.
Brad, where would you put that on the planned farm, whole farm returns?
In the middle. Sorry, whole farm returns. Oh, no, that's a good question. Go back and
What's
take
the
that question
feel?
on
Is
that.
it going to, from looking at that, that's going to be on the lower side? Is that fair assumption?
Growing. It continues to get more land and tuck it in and educate
A
kids.
bit more medium areas or a bit
Medium.
more up. Actually, the conversation we had and his gross margin seems to be in the medium to high range on the farms. Gross margins.
Because they rely less on debt and more on financing things themselves, and they don't commit to new machinery and do that. And they use their own they have young sons who are old enough to operate, mechanical and electronic things. They tend to have high equity. So
And then they'll go big debt when they want to take more land because they've got very steady income that easily be back. So they go hard and I'll go for it, but they're not going to go for things like highly depreciating stuff. They go for land. They continue to build that in. Yeah. Okay. Thing of organic carbon balance. They've achieved a low emission system. So we re-engineered the work that Richard Brake did using his numbers and came up with the same.
Richard Brake is
a consultant who does a lot of work in this area, and he ran the numbers on their system. For the purposes of our own skill development, we re-engineered that and came up with a very similar set of numbers. So Richard's estimate of the cohort that he's looking across somewhere between 1 to 1.5 tonnes per hectare of carbon, and this guy's sitting on about 4. So he's achieving that mission, and it's coming right out of the cropping side because they're very, very low inputs. And his livestock looks much the same as anybody else. An agronomist who works for elders estimates that his root matter is around twice the size of the pig. Probably again reflect a very good pH in the soil. We don't know what pasture root matter looks like. It would appear that whatever labile carbon he's producing, he's chewing up in his system. So that would be very interesting to understand what that looks like. Big question, is there an opportunity to sequester at depth? Use of other pasture ligands to get further down, store further in the profile. And again, this other question of biochar from straw mallees. This is an emerging bit for biofuels, and then there's also technology out there for producing electricity out of straw, ground cycle mallee. And then there's a big question of soil amelioration impacts on biochar. And the possibility of opportunity costs incentives. So, as I said, this case study is very near to the point where I start moving it out around for comment. We really look forward to digging into.
So what's the more story on the biochar? How does that work?
Well, it's a story. So carbon in 3 forms, like biochar. You produce wood, you turn it into an industrial process, produces wood for sale, the byproduct being the biochar, reincorporate back in the soil. What you get a very stable form of storage of soil organic carbon. But what else are the remediation impacts on the soil as well?
Isn't that very small increase in input back to that?
Yeah, it'll be continual year after year after year. If you're ground robbing, if you're growing these things, coppicing, and when you cut back a mallee, roots die back and they grow again. I mean, these are all questions to be examined and understood. And I think the same would go with cereal straw. You know, do we get alignment effect? Being very helpful. At the moment, we have a very bright young intern working, who's doing a research on this side. So she's here.
It's quite a lot of it's already been done on biotars, and most of it is pretty transferable. It depends what the source is and how it's been treated and how it's been produced. Is it what nutrients it retains, or whether it's just charcoal, or whether it's got a lining effect within it, or
So any of that data you have that we could also use part of this to build into the model would be terrific. So it gives us a handle on you know, what sources are. One thing I do know that from using straw, because it's very high absolute content, can't use activated carbon. Wood, on the other hand, what cheapy cost for putting it into that market might be too high for back into as a soil mill. We need to know what the relative values are.
Get closer to the microphone.
That's Chris.
And it's Chris. Any further questions?
There's been some questions online. I can read them out if you like.
Yep.
Is the greenhouse gas contribution from fertilizer predominantly from the manufacturing on nitrogen fertilizers or from the spreading of the fertilizers?
It's both. I would say about just for the fertilizer bit, as far as I know, about 20 to 30% comes from the manufacturing bit, while the rest of it comes from the spreading it.
I've also got legumes fix nitrogen and therefore sequences carbon as sinks. So why CO2 so high in model?
Legume does fix nitrogen, but there are, as you saw, the fertilizer input, the fertilizer aspect of greenhouse gas emission in legume-based rotation was a bit lower, but you still have to apply chemical and lime and rest of this stuff, which does have greenhouse gas emissions.
Great. And the last one, following on from Darshan's earlier comments about soil organic carbon, building and maintaining soil organic carbon is very difficult, especially in medium and low rainfall areas. Most soil organic carbon is quickly lost to the atmosphere. As such, using soil organic carbon to claim greenhouse gas carbon credits is effectively cooking the books. So that's a comment, not a question. From Brantley S.
Well, as you saw, we haven't actually got, as part of our charts and data, any claim on the soil organic carbon. We just at the moment we're just looking at what penalties you would have to pay for the greenhouse gas emissions. So we haven't yet priced the sequestration in. So we take that on advisedly, and we'll work with it. And we realize that there's not much of a soil organic carbon build up as we go along.
Okay, so essentially what I'll be doing, I have been doing the two main things. The first one is just to try to add this adding to the model that Susan built in terms of the body, build valleys in the field, and also using this straw bios, this biofuel or energy, and just to deploy it if we can, and I try to analyze this trade-off once we build the model. The second part is trying to model the southern ranges as a pastoral station, or a pastoral station as a whole. The idea is that we have been seeing a shift in the market to live export to domestic markets. This has a change in the herds structures, and also I have analyzed the implication of using a haystack. Haystack is the residual feed which stands in station, and it's not fed. You can have a look at that video to understand a little bit more what that's about. But the idea is to that haystack added to a conservative stocking rate will allow us to have a virtuous cycle in some A good case study would be analyzing the Alma Plains Research Station in Alice Springs, the Northern Territory. The idea is if we have a high stack conservative stocking rate, we can regenerate the land, increase the biomass production when there is rain, really variable rain, increase the availability of feed, increase the capacity, so we have a more productive system. We regenerate the land, and we can sequester even more carbon. So this is like a virtuous cycle we're going to analyze and see how it works. To do that, we have to model different things: livestock, micropods, other ferals, that interaction with the predators, if there are, and also the biology of the pastures, which is not easy. So that's what we have been. I will be working on. I have been working. That's all. Okay. Any questions?
Philip, I know Christophe is by trade a chemical engineer. It's pretty handy even to have a spreadsheet modeling and working on industrial processes such as electricity and biofuel production links into the farming system.
That was Brad. I don't know how many on the remote system heard. Brad was saying that Christophe also happens to be an engineer by trade, and he's now turned his attention to agricultural economics and farming systems modeling, or rangeland systems modeling as well. And so we're lucky to have him because his maths is better than ours, and he can also code better. So it's quite nice. So any other questions? Yes.
When you're doing the livestock speed study.
So I'll just run this over.
We need to give you that. But let's, okay.
So
That would be.
I think that's close enough.
Our television production studio, doesn't it?
I just wanted to know how much time it took to get that little detail for the livestock case study you gave through.
How long did it take? Oh, okay. A number of months. It's an iterative process, yeah, they generally take around 3 or 4 months to pull together if everything goes right. But often they'll take longer because, well, at the moment, for instance, this chap's away on holiday, so
Yeah.
you work around as people can.
And how long do you reckon we need to get that down to be able to be accounting this and use, like, I guess what I'm trying to say is to use it in day-to-day life, we need to be able to start measuring and having like that. So once we get this process evolved a bit more,
So
do you think the smallest amount of time it can take?
to what, to write a case study like this?
Not to write the case study, but so that people can get their farm in a way of presenting where they're at, tracking it, so that they can then start.
I guess I'm going to make a bit of a plug here, as with all of these things. The basic of all economics is information, and how quickly and accurately you can access that. And there's a great case here for some serious investment into some technology to lower the cost of gathering data and analysing it. So, with some technological development, I think we could just do a lot of this stuff really fast. But it will take time to put those systems together. So, for instance, in the rangelands, we were working on a project putting together a combination of citizen science and drone imagery using different spectral types of cameras and machine learning to be able to put together a body of information that could inform rangeland condition. It's just, that takes time to do that. Unfortunately, the person involved has got sick. We're one person thin. In a perfect world, if we had enough money and resources thrown at it pretty quickly. In the real world, we're going to pitch all this together bit by bit.
I thought that that question also gives us the opportunity to talk about a very important thing, is that the things, what's really good about modeling farming systems and in the way that it's been done here is the conversations that we have for gathering the data and the conversations we have in reporting our findings and exposing what is not known. if a model is really, really amazingly good, it often tells you what the farmers are already doing, right? But the value of a model like this is that it can help you see what is it that we haven't collected in the biophysical sphere that's stopping the economists from being able to put numbers, profit per greenhouse gas kilogram, or what profit per hectare, or profit per ton of wheat. Why is it that we are producing numbers that look surprising or dicky or just bad?
Because my thing is just, working in silos of like the consultancy of Plan Farm or Farmenco or the banks all having their own thing. Do you build upon those numbers and then, or do you go start from scratch?
No, we don't start from scratch. We always check against Plan Farm Plan Farm benchmarks. We also check against Farmenco benchmarks, which is another firm. We then, when it's ready with some numbers that we can defend or we don't find shameful, we take them to people like Rob Sands, Graham Laslett, Jeff Bosbury, and say, does this make sense? And then they often will tell you that there are logistical reasons, especially if they're innovations that we've evaluated. They'll often tell you why the innovation is not adoptable or something because of the logistical constraints. Ross can talk about this. But here we're not evaluating so much innovation. What we're evaluating is with and without carbon tax, emissions. And every time we go into these things, we find, and this is not a criticism, but then it is a small veiled criticism, in that often biophysical experimentation is done without ever involving the economists in the beginning, a bit like trying to do one of these things without a biometrician at the beginning. If we were allowed in the beginning to model the system, and then a project was written up to say, these are the things that would make economic change to the system if we studied them, then the right kind of numbers would be generated for an economist to be able to evaluate. Often, we get a really erudite scientist saying, oh, I evaluated the manganese deficiency of lupins. And we said, well, what would you do? Well, that's not going to help the economist, right? So that's nice. You've spent 10 years of your life doing that, but we need to know how lupin interacts with wheat and how lupin affects soil pH. What's your research question? So it'd be nice if economists were included at the beginning as well as at the end and during. And modeling like this helps answer questions that we wouldn't know to answer. And also, if the model is any good and if you're all happy with it, then what it does do is it stops you having to go and pay, Calix $30,000 to put a research plot from Geraldton, from Northampton to Esperance on different, spend literally millions of dollars with all the risk that goes with it of aborting the trials and the weather patterns, only to find that you could have just simulated it, basically. If I know not all of those things can be simulated, but some things can be done that can't be done in the field because it'll be too expensive. Some things can be done with simulations. Mandy.
Just a question on, I'll speak loudly if that's easier.
It does pick up most of the room.
Yeah. It's just a question on how you see the use of a value is going to happen. Is it a model a bit like Midas where you need one of you guys to drive it? So people need to you. Is that was one part of the question. The other one is you're doing it on a paddock or a field or a soil type basis. Do you see a value in taking a farm with, say, 7 or 8 different land units and then running the model for each of those and then bulking it up to get a whole farm picture and any interactions there?
So regarding first, I'll go to the first question about who will be using it. As long as we are not changing the assumptions, I mean, like we can teach someone like that where exactly is, for example, if you want to change the fertilizer price, you do not do that from the main Excel well, you just have to go behind and then change this fertilizer price. So that could be something we can help, but as long as I know, I'm confident about everyone should be able to use it as long as they know what are the assumptions they're making and what kind of consequences those assumptions will have. And then the farm scale level, we are thinking about it going to the farm scale level, but again, it really depends on what type of question you're trying to answer. So yeah, we could, if something could be answered by running the model 7 times and under 7 different farm scenarios, and then we can still get the answer, there probably is no point in building a proper farm scale model.
You probably know that Ross Kingwell, who's sitting in the room here, actually made a whole farm model that simulates 12 different seasons and comes up with the most risk-adjusted land use system for Eastern Wheat Belt. And that was called MUDAS, Model of Uncertain Dryland Agricultural System, which was a version of MIDAS, which was a model of integrated dryland agricultural systems. They get very big. If you want to put all those interactions in, you know, what happens with wheat after lupins, what happens to 2 years after wheat, if you grow wheat again, all that sort of stuff, and how does sheep utilize the pasture generated and all that, how do sheep move around the farm, all that sort of stuff gets really tricky. And so it's essentially skill limited, right? So, and the commitment of the organization to fund and maintain, and not just this organization, but RIRDC, GRDC, HORT-RDC, and this department and the universities that also draw on this sort of modeling work, and CSRO, is to maintain a body of people that can do this. These are rare as hen's teeth, these people. And they necessarily move to where there's best superannuation, best money, and all that. So we're competing with mining and oil and gas, and to some extent banking. I'm saying that if you've got the right people, so you don't so much need a model, you need a good modeler and good analyst. In fact, we found with MIDAS that the model could be written by a good modeler and an analyst could adjust it. But you mustn't let loose just anybody, and not anybody could be made an analyst. I'll make a distinction between a modeler and an analyst. So Ross can make the MIDAS model, which is very sophisticated, but for someone to be able to use it requires a lot of care and attention, and they need to be co-housed and accompanied for several years by Ross before you let them touch that thing, because it's like a sharp knife, you know, or it's like a, you know, it's like a big machine. They'll get their fingers caught in there. They'll have to repeat it again. You ask Sudarshan how many times the model that he's made and he understands completely, how many times he's had to repeat the runs he intended to show you today. It's because you forget to put this in, you forget to put that in.
About 3 days.
Anyway, it's been lovely to have you with us. Thank you.